Hello, everybody.
Hello.
Okay. Okay, so today we are still dealing with obviously test 1 material. I have seen some people have been attempting the naming quiz, which is good. I like that. I like it a lot. Make sure everybody's got their video on, please. Okay. Let's see where we're at here. Excuse me. Oh.
Bless you.
Thank you. All right. That's right. We had just dealt with Friedel-Crafts alkylations and acylations. Now we're looking at reactions of phenols. Now on the test, you'll get one of these reactions of phenols, but I'll tell you it won't be. It'll be either A or B. I won't give you C. So it'll be one of these two.
Did you say B or C? I'm sorry.
It'll be A or B, but not C. So it won't be this one, the Rhimatimian reaction. Okay, it'll be one of these two, A or B. So the way that the Williams the way the Williamson ether synthesis works, this is the one that you've seen before. You would have seen it back in Organic 1, and it enables you to take a negatively charged oxygen and add it to an alkyl bromide, but the alkyl bromide needs to be primary, and that produces an ether, but it's specifically a phenyl ether. Now the thing with phenol with the OH on it is that the H is quite acidic. And the reason for that is because when it forms an anion, it forms an anion that is stabilized by resonance with the aromatic ring, which makes that anion a bit more stable. The consequence of that is that we don't need a very strong base in order to remove that hydrogen from the oxygen. So even something like sodium carbonate would be a strong enough base to take that H off and form the negative charge on the O. The mechanism for the next part is just the O negative coming in and attacking the CH2 on the alkyl bromide and kicking out the bromide. So that would be an SN2 kind of reaction. It's a fairly simplistic kind of reaction. Does anybody have any questions about this one? The other possible reaction you might see, this would be as part of question 1, by the way. You'll just get one of these, either A or B. And again, we've got the Colby synthesis, which is the phenols. I've got here, phenols are acidic. So the deprotonation is facile. So what I'm saying is that this part here where the H is coming off the O is very quick. So what happens is that the carbon dioxide here is just dry ice. It's chunks of dry ice. You've seen solid carbon dioxide before, and you throw that in with the sodium hydroxide. And yeah, this is a good way to make what we call salicylic acid, which is this OH with the carboxylic acid, this benzoic acid group in the ortho position. Now it goes in the ortho position because and not the para position. And we'll talk about that in a bit, but it goes in the ortho position because the C here is a lot more negative than the C down here. It could possibly add as a para, or at least looks like it could. But because this C is a lot more negative than this C, it goes in the ortho position. So there's a lot of stuff going on here. The product is salicylic acid, but the mechanism here is one you can learn if you want the bonus point for that question. So I said that you'll either get this one or this one. Does anybody have any questions about B, the Colby synthesis?
Can you explain the ortho or para position one more time?
Okay, the ortho position is this one here, the one next to the C, next to the OH. The para position is down here. If you look at the way the arrows can go, let me show you something here. I don't want to confuse people, but I'm just showing you why I mentioned it. Keep in mind this doesn't happen, right? Now the para position's down here where I put the arrow, but you'll notice that I can draw arrows that might lead to that, but it doesn't happen. And that's because the C here is a lot more negative than the C over here.
And it's more negative because of the negative charge of the oxygen that can shift.
Well, it's just closer to it.
Okay.
All right, any other questions? Okay. So the Rhimatimian reaction is another one, but you won't see this on the test. This is a way that we can create salicylaldehyde, which is only different from the previous one because that's an OH and this is an H. So this is an aldehyde, not a carboxylic acid. And it uses this creature called dichlorocarbene, a very electron deficient species, in order to react with the aromatic ring to form the aldehyde group. I'm not really going to go into that, but it's a very complicated reaction, as you can see here. All right, I'd like to focus now on aromatics and how we deal with the second substitution. So what I'm talking about is a situation where we already have something on the ring and we're trying to determine what kind of product or products we're going to get after we've reacted them with an electrophile. So there's two cases that we're going to deal with here. Both of them involve something already on the ring, which I'm calling this magical group X. Now, if X is what I'm calling activating, then we're going to get a mixture of products. We're going to get ortho and para products. Remembering that ortho is a Y group directly on the C next to the X, and para is the Y across from the X. So that would be ortho, this one would be para. And if X is what I'm calling deactivating, then it's going to be, the product's going to be, only one product's going to be the meta. So let's talk about what makes a group activating or deactivating. So the top reactions, the ones that are directing ortho and para, have what I'm calling an activating group, and activating groups will tend to push electrons into the ring. Deactivating groups will tend to pull electrons out of the ring. So what matters is whether X is one of these groups. Doesn't matter what Y is, all that matters is what X is. So whatever's on the ring is what is going to direct where the reaction's going to go. So let's talk about activating and deactivating groups. So activating groups, as I said, are anything, well, I've got it up here. NH2, NHR, NR2, OH, OR, alkyl, or RC double bond O, NH, where the connection is through the N. All of those are possible. And the way that these push electrons into the ring is because they either have a lone pair of electrons, or in the case of the alkyl group, they can push electrons into the ring via what I'm calling hyperconjugation. And hyperconjugation is the electrons in the C whatever bond. Let's see if I can draw that a little bit more detailed. It doesn't matter, C whatever. Let's say it's CH, for example. So the electrons in the CH bond can actually be donated to increase the electron density of the aromatic ring. So that's what I mean by activating. All of these do the same thing. They've got lone pairs, or they've got hyperconjugation that allows for those to have electrons added to the ring. Deactivating groups do the opposite. They pull electron density out of the ring. You'll notice they all have something in common. So I'm going to expand this a bit. Look what all the deactivating groups have in common. Either they have a delta plus on the C or N or whatever, or they have a full-blown positive charge. And this is on the atom directly attached to the ring. So because of this, the electron density ends up getting pulled out of the ring. And that's what they all have in common. But you'll also notice that it's atoms that are usually, except for the middle one here, multiply bonded to the atom that is directly attached to the ring. So if you've got an electronegative atom multiply bonded, either double bond or triple bond, to the atom that's on the ring, then that's going to lend it towards being a deactivating group. This one here doesn't have a multiple bond, but it does have a positive charge on the nitrogen, which allows you to see how electron density could be pulled out of that ring as well. Does anybody have any questions? Okay, let's look into some of the theory as to how the activating and deactivating groups will influence the kinds of things we have attaching to the aromatic ring. So we're focusing here on activating groups. So as you can see, the product, if X is activating, that means X is already on the ring, X is an activating group, the products will be ortho and para products. So let's look at why ortho and para products are going to be favored if X is activating. In the first step, when the electrophile adds to the aromatic ring, you'll notice if we do it ortho that the plus will appear at the other end of the double bond where the E ends up attaching to the ring. So we have an E attaching on the ortho position to the X group, and the positive charge ends up directly on the C that's under the X. Then what can happen is you can see resonance occurs. So we've got these arrows here. So the arrow shows the movement of a double bond to put the positive charge in the meta position to the X, and then another movement will have the double bond move over to the other meta position, and then we can lose H plus, and that's how we would end up with our ortho compound. So all three of these are what we call resonance structures that show the movement of the positive charge as it goes around the ring. The important point to note here is because the electrophile has gone here in the ortho position, it is possible to draw a resonance structure where the positive charge is directly underneath the X. Now, because X is activating, that means it's pushing electrons into the ring. And if it's pushing electrons towards a positive charge, that's a stabilizing type situation. So the very fact that X is pushing electrons into the ring means that this is what I'm calling a favorable resonance structure. Does anybody have any questions so far? I'm going to say a little bit more about the resonance arrows here and what they're doing. So you can see that if I move these two electrons from the bond that I'm showing you here to the other bond to form a double bond, the effect is that the positive charge will end up moving to the location where the double bond was located, and the double bond now will be in between the two C's that are next to the X. Does anybody have any questions? And that's how the resonance works. You'll notice that these are double-headed arrows because we're showing resonance structures, and then this is a single-headed arrow because we're showing a reaction here, the H plus leaving and forming the ortho compound. You'll also notice that when we attach the electrophile at the para position, it leaves the positive charge next to the C that has the E on it. Then we can move the electrons around, and you'll notice that we can draw a resonance structure again where the delta minus is above the plus, which is a stabilizing situation. That's what makes it a favorable resonance structure. And then we can lose the H plus and we end up getting the ortho position. So both ortho and para have situations where the X group can stabilize a positive charge because of where the electrophile has attached to the ring. In the case of meta, you'll notice that we put the electrophile on and we can draw the positive charge in, but you notice that we can't draw any situations where the positive charge is directly under the X group. That means the X group doesn't really have much of an effect in stabilizing that positive charge. So what I'm saying there for the meta is that there are no favorable resonance structures. So what happens is that the activating group directs ortho and para because there are favorable resonance structures that are involved when the electrophile attaches at those positions. However, when it attaches at the meta position, we don't see that. So it doesn't form meta. You'll notice there's no arrow here because we don't see the meta. Does anybody have any questions? Nobody has any questions about this, hey? Shocking. Is this thing on?
How will we see it on the test?
It's a good question, Bailey. And I will answer your question, but not right now.
So for the favorable resonance structures, we're just looking at where the plus is.
Courtney, can you repeat that, please?
So when we're looking for the favorable resonance structures, are we just looking at where the plus is?
Yeah, in relation to the X.
Okay, so if it's right beneath the X, that's what makes it favorable in the activating?
Yeah, because if you've got a plus and you've got a delta minus or a negative above it, that plus negative thing's a good thing.
Okay.
I want you to contrast that, Courtney, with the one I'm going to show you next.
Okay.
But Bailey, just to give you just to scare you a little bit, yeah, you will have to do something like this on the test. But you'll see in a minute what that looks like. But I know you're scared already. Maybe not. Maybe you're not scared, but some other people might be. We'll see. I scare people. That seems to be what I do. All right, deactivating groups. Let's see. You'll notice that the resonance structures now are exactly the same as what we were dealing with the activating groups. What's changing now is the nature of what was favorable is now unfavorable. Now, what makes this unfavorable? So if you've got a deactivating group, effectively what you've got is a partial positive on the X because it's pulling electrons out of the ring. So if you draw situations now where the positive charge is directly under the X with the delta plus, that is going to be a bad situation. That's going to be unfavorable. Positive, positive is unfavorable, whereas positive, negative would be favorable. So again, these resonance structures are exactly the same, but what was favorable is now unfavorable. Does anybody have any questions so far? So
you said, I'm sorry, you said positive, positive is unfavorable, positive,
yes.
negative is favorable.
Yeah.
Okay.
Yeah. You know that like charges repel and unlike charges attract, right, Keisha?
Yes.
Yeah. So we're just applying that same principle here.
Okay.
So you can see that when we attempt to put the electrophile in the ortho and the para position, you'll notice that we don't get ortho and para compounds because we do get the possibility of forming these unfavorable resonance structures. Again, these were favorable when X was activating and was partially negative, and thus favorable. Now the X is delta plus and unfavorable because it is unfavorably interacting with the positive charge on the ring. However, if we look at the meta position, there are no unfavorable resonance structures. So it goes meta because ortho and para are unfavorable. I want to point out from a semantic point of view that no unfavorable is not the same as as favorable. No unfavorable is not the same as favorable. It's just that there are no unfavorable resonance structures when we go meta. What that means is that meta is usually a bit harder to make than ortho and para because you're trying for the default here, the one that isn't particularly bad, rather than the others which are bad. Does anybody have any questions?
So it's like a default setting, pretty much?
Yes, I'd say it's a default, yeah. It doesn't go ortho para because they're bad. Whereas activating goes ortho para because they're good. So I want you to be able to make that. I want you to be able to make that comparison.
So when we see the delta plus, like during the deactivating group or like the delta plus or the delta minus in the activating group, we should know what our product should be based on what the charge is.
It's a little bit trickier than that, Bailey, because I'm not going to tell you if it's delta plus or delta minus. You'll have to know based on the group.
Oh, okay. That'll make sense.
Okay, so knowing if it's activating or deactivating is based off the group attached to the aromatic?
Yeah, see on this slide, Courtney?
Yes.
So you'll see these are the groups that are activating, you'll see the other ones that are deactivating. And again, what's important is the partial charge on the atom directly attached to the aromatic ring.
Okay, so on the test it'll be one of those. Yeah.
Yes.
Okay.
But I'm going to write this down here because I think it's worth putting down. Okay. So whether a group is activating or deactivating, depends upon the partial charge of the atom directly attached to the aromatic ring. Does anybody have any questions about what that means? So delta minus equals activating. And delta plus is deactivating. Now I hope that's just not words. Does anybody have any questions about that?
I understand what you're explaining here, but for the activating group, the one that is just a carbon,
Yeah.
How would you, I mean, there's no electron I mean, how would I know this has a partial negative charge? Because the rest of them either have, extra pair
I
of
know.
electrons.
I know. You have to know that hyperconjugation is possible, Mary.
Okay. Can you explain hyperconjugation? We had it in Orgo 1.
I did explain it earlier. I erased it off this page before I had it. But it's the nature of it is that if you've got a C connected to an H or even a C, the electrons from the CH bond can be donated into the ring. It's not a very big effect, but it's enough to cause the activating effects to occur.
And this would be the only case?
So yeah, well, you mean the only, yeah, I guess
Yeah,
so.
For example, so the examples you have here, I'm sure, are not the only electron donating or withdrawing groups. For me to kind of realize.
Well, they're all here. These are the only ones that you'll have to deal with, really. Do you see them there?
Yes.
All right. Okay, let's talk about the test question here. So Bailey, I'm going to answer your question now. See, I didn't forget you. So what we're talking about here, I think it's question 2 or 3. I think it's 2. Here it is. I'm actually kind of nice about it because I give you all these little templates to draw the things in. So what you have to do in your first mission is to look at the group and determine whether it's activating or deactivating. This one happens to be deactivating. So then you would go ahead and you draw in all your resonance structures and you would figure out which one it forms. It'll have to be the meta that it forms. You wouldn't draw any arrows in here because it doesn't form the ortho and the para. Or over here you would, and over here you'd probably want to put what it forms, which is the meta one. And then you would draw in, again, you'd figure out which ones were favorable or unfavorable resonance structures. In this case, unfavorable. And that would come, that's how you come up with the answer there. So I'll just show you the key to that so you can see what the answer looks like. All right, so you can see what they've done. They've got unfavorable resonance structures and then no unfavorable resonance structures or resonance structures on this bottom one here. Anybody got any questions?
So you could tell that it was deactivating since the aromatic is directly connected to a C, which has a delta plus. Correct?
That's right. And we know the C has a delta plus because it's directly connected to a double bonded oxygen.
Which is a delta minus.
Which is a delta minus, which puts the delta plus on that C, yeah.
Okay.
So as a general rule, I mean, it's pretty easy to tell. If you've got a C here or even any atom here that's multiply bonded to an electronegative group, it's going to have a delta plus on it. So in general, you can pretty much say this. And then for the most part, everything else so if you've got something like this, actually, hang on. So if you got an atom attached to the ring and it's multiply bonded to an electronegative group, and I've got either a double or triple bond here, then that's going to be deactivating. The other situation that is deactivating is this situation. That's deactivating as well. Pretty much everything else is going to be activating, and you'll notice that those will generally be these situations here. O, N, and alkyl. And you'll notice that these are not charged. And all those cases will be activating. Okay, does anybody have any questions?
So the ones you just drew with the O, N, and R, those
Mm.
are
Yeah, that's right. Yep. So I don't know. I don't think it's that big a deal. I mean, to look at this is something that obviously people have conniptions over all the time. You know, oh, I don't know if it's activating or deactivating. How do I tell? It's not really that big a deal. I honestly, I don't think it's that complicated. Does anybody have any questions? Or does anybody disagree? Does anybody think it's really complicated? Activating, deactivating groups? All right. Okay, that's good. So obviously in question 2, you could get an activating or a deactivating group there. Okay, this one just happens to be deactivating. But they all use bromine, Br2, FeBr3 as a reactant. So there's never really any variation there. It's just about the group that's already on the ring. So any other questions? Okay, let's do a little practice here. So this is the blue book, or whatever I'm calling is the blue book. So I still got to bash some heads over the bookstore not having it. All right. So if we start on page 28, what I'm going to do is I'm going to go through and I'm going to point at some, and I'm going to see if you all can figure out if they're going to be activating or deactivating. Some of them are not reactions we haven't seen yet, so don't panic. All right, let's take a look at number 3 there. So what do you all think? Actually, before I do that, let me draw this out a little bit better so you can make a better determination. So the NO2 group, if you drew it out, actually looks like this.
Aha, so deactivating, right?
Yeah, so that one's deactivating. I'll put a D underneath it. All right, any questions? Can I let me point something else out as well. All right, before we move on with that. So when you're looking at solving these kinds of problems, you look at the reactant as well. And that's H2SO4, HNO3. And what you'd have to know is, based on what we had talked about, the electrophile from that is going to be NO2+. Now, the nature of this electrophile doesn't affect where it goes on the ring. The only thing that affects anything is what's already on the ring. So because this is deactivating, it's going to go to the meta position. So the product is going to be the meta product. So that would be the answer. Does anybody have any questions?
Yeah, I have a
Yeah.
question.
Yeah, Julie.
How do you know that it's going to be NO2+? How do you know to pull that out?
Okay. I'm going to take it back. Oh, I don't want that one. Hang on. So this is from. Yeah, I'm going to go back here. I'm going to show you. And somebody had asked me. Here we go. All right, take a look. See nitration there, number B? Julie?
Yeah, I'm trying to see it. It's kind of small.
Oh, okay. All right.
All right, I can see it.
All right. So that's how it forms that NO2+. But you'd have to know that. You'd have to know that that's what it does.
But I could probably guess that it's going to take water out of it.
Yeah. Oh, I don't know about guessing. Maybe you just know.
I mean, even if I didn't know that exact mechanism, I would probably be able to say, well.
Well, that's my hope.
Yeah.
That's my hope. Is it a dim hope? I hope not.
It's medium dim.
I hope
No,
it's
I
not.
mean, medium dim that I could remember that mechanism in particular, but it's not dim that I could look at it and say, okay, well, you're probably going to take the H plus out of the top and an H2O out of the bottom.
And there you go. That'll work. That'll work. All
Okay,
right.
that I could probably do.
Okay. And by the way, Julie, I wasn't calling you dim. I promise.
No, that's okay. You can call me dim. It would be accurate. Thank you.
All right. Let's take a look at the next one there, number 4. Now the Me here, well, it's not me. Me is methyl. My chemical drawing program thinks it's smarter than I am. So whenever I put OCH3, it just changes it to OMe. All right, activating or deactivating?
Activating?
Activate.
Yeah, that's activating. You'll notice there's no double bonds or anything to it. We've got an uncharged electronegative atom, so we know it's pushing electrons into the ring. So if we take that same logic, H2SO4, HNO3 being NO2 plus, the products are going to be the ortho and para products. Okay. So that's what you get. And that's what you'd put down for that. Now, I'm going to show you something else here. They're not formed equally, by the way. This would be about 64%, and the para would actually be about 36%. Interesting. Interesting. There's a really simple reason for why this is. Does anybody know?
There's 2 ortho positions and only.
Yeah, that's it. Yeah, that's the reason. Yeah, there's 2 ortho positions because of symmetry. You got this one here, and you got this one here. But there's only 1 para position. So it forms in a ratio of about 2 to 1. A little bit less because there's a little bit of hindrance from the OCH3, steric hindrance. It's a fairly big group, so it kind of blocks a little bit of the NO2 from coming in. All right, anybody got any questions about that? All right, let's have a look at another one here. Oh, yeah, let's look at number 6. I'm going to draw this one out so you can see it a little bit better. I'll draw it out as a line structure. So what do you think, activating or deactivating?
I want to say activating.
Yeah, because there's no double bonds or anything to it. So again, that's just going to push electrons into the ring. And now the other one, so Julie, you had asked about the H2SO4 and the HNO3 and knowing how to pull that out, right? But this one, I'll show you exactly how to pull it out. So the AlCl3 takes the Cl, and then the rest of it becomes your E+. So really, this is, that's the electrophile right there. Any questions? Any questions? Nobody has any questions about that? I'm really surprised. Shocked, actually.
what comes out of it's still kind of confusing sometimes, but I haven't memorized it yet.
Oh, and that's I don't like the use of that word. I'm sorry. I do have something against the use of the word memorizing. Maybe you haven't understood how the reaction goes yet. That might be a better way of putting it.
Yes, that's what I meant.
Yeah. Let's go back to it. If you look at all of these things that involve the AlCl3 or the FeCl3, they all have something in common. The first step always involves removal of the halogen, and whatever's remaining gets a positive charge on it. And that's what we're seeing here. So it's just application of that. So the products for this one, since it is activating, there's going to be two products. There's the ortho product and the para product. That doesn't look pretty at all. So that's your ortho product. And again, the connection point is to the C that has the positive charge on it. All right, so you got your ortho and your para products. Does anybody have any questions? Anybody have any questions? All right, take a look at number 7. Activating or deactivating?
Deactivating.
Yeah. What's the big clue for you, Donna?
When I see double bonds,
Well,
off the C.
let's be more clear, please. When you see
Okay.
double bonds, where?
Off of the carbon that we're looking at.
Which carbon are we looking at, Donna?
We're looking at the one attached to the benzene.
Yes. Yeah. Notice how I'm being really picky about that.
Absolutely. So no, the double bonded so the double bonded oxygen has a partial negative, which means that that carbon is going to have a partial positive.
That's right. Which pulls electrons out of the ring. When we look at FeCl3, and I'm going to draw this out as Cl for kicks here. So that gives a Cl plus, and this is going to give one product. Which is the meta product, since it is deactivating. Any questions? What about number 10? Activating or deactivating?
Activating.
Yeah, because it's an alkyl group. If I draw it out. So Mary, you had asked about this earlier.
Yeah.
So it's the, yeah, it's these electrons that can get donated to the ring. So you got FeBr3 and Br2. And so it's Br plus. So the products, there's going to be 2 of them. We've got this one and this one. Any questions? Any questions? All right, so at least you're getting an idea. I'll do one more. I'll do 13. 13 is an interesting one. Oh, I like 13. Now 13, I'm going to have to draw this out a bit for you so you can get a clearer view of what the group on the ring actually looks like. And it's HNO3 and H2SO4. I'm just going to go ahead and put NO2 plus there. We talked about this. All right, activating or deactivating? Oh, actually, I'll tell you what, I'm going to do a poll here. Hang on, do a poll. Hang on, stop. Don't go anywhere.
Can I ask a question?
In a second. In a question. In a second, sorry. Hang on. I can only do one thing at once. I don't multitask very well at all. Okay. All right, 2 seconds, and we'll get to this in a second. Polling, here we go. Launch poll. All right. So, activating or deactivating?
Do we need to press somewhere?
Yeah, I've made the poll
Oh,
available.
yes.
You
Sorry.
should be able to see it. I've had 14 people answer it already, so somebody can see it. All right. I'll give you another 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. End poll. Here we go. All right. Oh, look at that. Can you all see that? Can you all see what I'm sharing? Okay. So 18 of you said activating, 10 of you said deactivating.
It's funny, the percentage is actually the percentage of the products for activating.
Oh, yeah, yes. Yes, that's hilarious. Yes, we can laugh about that for ages. All right. I'm going to stop sharing that now. Okay. But yes, that's correct. It is going to be ortho and para because it is activating. Now, I know why some of you said deactivating because you saw this C double bond O. Can anybody tell me the wrinkle though here?
Is it because of the, like, what's attached to it is what's like an activating product?
That's right. See, if the C double bond O was attached to the ring, yes, I'd say it was deactivating. But since the N is attached to the ring, then that's the one that's activating. And that's why you're going to get the ortho and para products. And yes, they will have that same percentage as we had in the poll, which is true. All right. Does anybody have any questions about that one?
Yeah, I do.
Yes, Julie.
Okay, so my question was when you wrote that out, you know, you see this thing and it says CH3CONH.
Mm-hmm.
And like you right away knew that that N was, of course, connected to the ring. But
Yes.
I looked at it and I just saw CH3CONH and I said, okay, what's connected to the ring?
Right.
So is there like a quick way to know that, or do you just have to really know what you're doing really well to, I mean, now that I'm looking at it, I can see why, but it didn't like read that way to me when I looked at it.
Okay. So yeah, you had it right, but the N is directly attached to the aromatic ring. So you're okay with that, right?
I'm okay with it, but I didn't know it until you
No,
drew
listen.
it.
No. But you're okay with the N being directly attached to the aromatic ring, correct?
Yeah, I'm okay with it.
Well, going back to the I mean, it's really just the CH3CO part you have issues with, right?
I guess. I mean, I know the CH3 wouldn't be attached to anything other, well, no, it's going to be attached. Well, no, I guess it could be.
Well,
But
you
then it
can
was in the,
well, look, you can see the diagram's clear on this point, but the aromatic ring is connected to the N, right? I mean, that's because it is, right?
okay.
You have to agree with me on
But
that
how would
point.
I agree with you, but how would I just know that by looking at it?
Because the line is to the NH, so it can't be to the H, so it must be to the N. Do you see what I'm saying? Because it's
And
in
it
that
can't be to
order.
the-
Because it's in that order, Julie.
Okay. And it couldn't be to the H because there's only one bond to the H.
That's right.
It has to be connected to that. All right.
Yeah. I think that answers your question. But your other deeper question is, how would you know it's CH3 C double bond O? Is that what you're asking?
Well, I guess I just looked at that and it just, you know, it wasn't like a familiar thing. I see CH3CONH, and that's not like something like you see it, you know, all the time. So I'm looking at it going, okay, well, what is that? Where is that attached to the ring?
All right. Now, the thing is that these carbons are all assumed to have 4 bonds. And the way it's written, if it's CO like that, you know it's a C double bond O, because there's no other way that it could be and have the C have 4 bonds. So it has to be a C double bond O.
Okay. Okay. So I guess you just sort of have to look at it and break it up and then say, okay, how are these going to look and where these? It's just that you did it so fast, and I'm looking at it going, like I wouldn't automatically do that.
Yeah, it's almost like it's organic too, and I kind of expect you to know that.
I know.
I know. Yeah, that wasn't very nice of me. I'm sorry, but that's how it is.
It's a sad thing.
It is sad.
I agree.
So if you've got something like this, I would want you to know that it was really this. If you've got this, whoops, I'd want you to know it was this. If you had this, I'd want you to know it was this. So that's kind of stuff I expect you to know. All right. All right. So if you want to, you can go back and look at this another time. But yeah, this is, we're rightly or wrongly, I've assumed this knowledge because you're inorganic too. I'm not just talking to you, Julie, I'm talking to everybody. Does anybody have any questions? Okay, does anybody have any questions?
So what about number 5?
What about number 5? Well, number 5 we haven't done yet.
Okay.
Is NBS, we haven't done it yet.
Okay, cool.
All right, any other questions so far? There are a whole bunch of other ones here as well, but you know you can go through those yourselves. There's answers to these as well.
So for these kind of questions, we always only have one substituent coming off of the benzene ring. It can't have 2 and then we add a third one.
Yes, we can, and we're just about to do that, Mary. It's a fantastic segue. I'm so glad you asked that.
Okay.
Because people don't like these either. But anyway, let's have a look. All right. we've kind of been through this, or at least I showed you this when we were doing the NMR. And we noticed that there's some interesting things that happen with directing effects and peak distribution in the aromatic ring when we're talking about proton NMR. So when you've got a strong deactivating group like C double bond O, NO2CN, S double bond O, you'll notice that it splits the aromatic ring into two peaks. And the peaks are centered at around 7.5, or maybe a little bit more than that. And if it's an activating group like O and N, then we tend to get, again, two sets of peaks, but they're centered more around 7 ppm. And then if it's like an alkyl group, which isn't really that strongly activating, it's very weakly activating, we tend to get just a single peak. So that's just something you'll notice in the NMR that we can get. And it can be useful, especially when you're trying to put a structure together and you're trying to figure out what's connected to the ring. The peak structure, or how the peak distribution, can be at least a clue as to what is directly attached to the aromatic ring. So it's just something to think about. All right, Mary, you asked for it. Here it is. Third substitution. So, you know, we've been talking up to now about second substitutions. What about third substitutions? Oops, wrong one. Let's go back over here. There we go. So you'll notice that for certain kinds of third substitutions, we can get predictable products, but for others, we can't. I mean, it's much harder. Let's take a look at the situation where we've got an activating group and a deactivating group directly attached to the aromatic ring, but in the ortho and para positions. Okay, so I'll write that as A, that's D. And if we would use our HNO3, H2SO4, so that's the NO2 plus. So what we do is we look at these and we figure out where these are going to direct. So the O, because it's activating, is going to direct ortho. It can't direct para because there's already something down there. So we're not going to end up substituting that group out. So the activating group is going to go here, direct here. The NO2 being deactivating is going to direct to the same locations. Now, because this is symmetric, we only get one product. And that will put the NO2 group over here, or it could go on the other side where I've got the other stars. But that's the only product that we're getting. So that's not a negative, by the way, that's a methyl group. Anybody have any questions? If we're dealing with activating and deactivating groups that are ortho to each other, the activating group will direct here and here, so the ortho and para positions. The NO2 group will direct to the meta position of the NO2 group. So that's how we end up with those two products that are shown in the slide. Anybody got any questions?
So NO2 is deactivating.
Yes.
It would give us only the meta position.
To the NO2 group, yes.
Oh, there are both two products. Okay, got it.
Yeah. Well, no, there's two products there for the second one I showed you. There's only one product for the first one, Mary.
What do you mean for the first one?
The one I'm pointing out with my cursor.
Yes, because both possibility falls on the two same positions.
Yes, that's right. Because because of symmetry.
Okay.
And the last one there, if you've got two deactivating groups, you can possibly put a third group in the meta position to both of those. But again, that's tough. I mean, if you've got two deactivating groups already on the ring, then you are really sucking the electrons out of that ring, and you may or may not get that to work. That is a really tough one to get going. So if you've got two nitro groups already on the ring, it's nigh on impossible, because those are such strong deactivating groups, to get the NO2 group to go in the third position. You can do it, it just is really low yielding. It's really hard because these nitro groups are already sucking electron density out of the ring. And you're trying to get them to react with something that's positively charged. So you can get it, but it's very difficult to get it. Now, one thing you can do is, if you've already got an activating group on the ring, like a methyl group, then you can get this to go a lot more easily, because now you've got an activating group on the ring. But you'll see that this will direct where? Down here. The only place it can direct is here. The NO2 groups are already in that position. This is not one we like to do in the lab. Any ideas why?
It's TNT.
It's TNT, trinitrotoluene. Yeah, one we like to avoid. There we go. So that's TNT. All right. Any questions? I think this is probably a good place to stop for today. If anybody wants to hang around and ask me anything, they certainly can. And for the rest of you, I'll see you all on Thursday.
Thank you.
Thank you. See you all later.
Have a
Bye.
good. Bye-bye.
Thank you. Bye.
No worries. Bye. Jasmine, Sylvia, do you have a question? You're okay?
I'm good, thank you.
All right. Jasmine, how about you? No, she's gone too. All right.